Hi, this is Waitong Matthew Leung. I am an online graduation student in MCS Data Science program, and this is a presentation of my final project of course CS 598, Deep Learning for Healthcare. The topic of the final project is called Drug Review Sentiment Classification using Deep Learning Networks with Attention Models. So the overview of this presentation is I talk about motivation of this project, the data set that we use, and some basic deep learning components that we use in this project. And then finally, some proposed sentiment classification models. So what's the motivation? So sentiment analysis is a really popular natural language processing technique to automate mining of like user preference or perceptions. For example, it's really popular to use this technique um, to mine newly launched product from these like real-time monitoring on the social media text. And we can use the same technique to predict user sentiment on drug review text as well. So we can use this automated classification to discover like drug effectiveness, side effects, and possibly some interaction of multiple drugs. So, for example, there are few emergency released approved COVID-19 vaccines. We can automate the process uh, to to mine the text of user review to see any adverse side effects from these new vaccines. So the data set we use is from UCI Machine Learning Repository. The data set has split into two files, like one training set and the other is test set. It's 75-25% split. Total number of reviews about 200,000. So we're gonna talk about some deep learning components that we use in this project. So what is word embeddings? So there's one simple way to encode some features is to use like one hot vector. Right? Let's say this a doctor's visit diagnostic would be headache, uh, 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 what stomach ache, and some other things. Like each of these diagnostic uh, can be represented by like one bit in this feature vector. But the problem is like these diagnostic vectors, they have the same distance. So similar diagnostic, they don't really come together or represent closer in the representation space. So the idea of embedding is like to encode these features with similar concept closer together. Let's say a patient with COVID-19 might have like obesity or like high cholesterol and all these other symptoms or diagnostics, like the representation of these diagnostic going to be closer together in the presentation space. Um, and this is really useful to do the prediction and regression in machine learning models. And we can do it in similarity search to find similar concept, and also do some like algebraic operation among these like embeddings to get some better understanding of combination of concepts. For example, queen is equals to king minus man plus woman, and this is a visualization of that example. This is the king representation and you minus man, you get this vector here, the doctor vector here. If you add this doctor vector to women, then you get queen. So this is kind of the visualization of that embedding example. Next, we talk about deep neural network. So neural network is a really powerful function approximators that learn from training data to map input data X to output data Y. The usual applications for classification and prediction. Neural network is a fully connected network of basic unit called neurons. And neuron is a computational unit that inspired by our human brain neuron. So it has the linear transformation part that transform an array of input with the associated weights and then apply nonlinear activation function. Neural network with one or hidden layer, we call it deep neural network, DNN. So this is an example for neuron representation for NAND gate. So what is a NAND gate? Basically, the two input can be, each of the input can be 0 or 1. For any combination, the output is 1 except input 1 and 1, then we get output 0. So you can see that like if we input 0 and 0 here and multiply by the weight, this is of -1 and -1 is 0, but we add the bias of 2, then the linear sum is 2, and then we feed it through this nonlinear activation function, which said that if X is greater than 0, then we have output of 1, otherwise output is 0. So you can see that this is kind of the output basically is like implement the NAND gate behavior, and the training of neural network basically is to extract the information from the training data to learn about the weights here, the weight of 2, -1, and -1. And this is a visualization of another deep DNN with hidden layer, input layer X, output layer Y, and hidden layer. And just talk about some variant of DNN. So convolution neural network is a really popular one for grid-like data, like images or time series. So the difference of this is to DNN is like this one creates some local connection to a hidden unit in the next layer, which is like we call them filters, and the output is called feature map. And a CNN has like way less connection than a fully connected layer. The number of hence the number of parameters need to be learned is much less than fully connected like DNN. And there's some concept that in CNN, it's like translational invariance means that like some local region feature we can apply to global regions, and compositionality means that we can compose some low-level features like lines and curve to make some high-level representation like face. So this is one example of like convolution. So this is a input data is in a grid, and then I have a 2x2 filter. And if we apply the filter to this patch here, the first four grid here, and then move it to right, the second patch, and then move it down. And this example here is like apply the filter on this particular patch. So you can see that like applied multiplication of 1 to 5, 0 to 6 and 8. So basically you're just adding up these two numbers, 9 and 5, become the output of this feature map of 14. So the next one is recurrent neural network. So this variance is good to model variable length of sequential data. Uh, Order makes a difference. Uh, let's say like human language, natural language, like order makes a difference. And the output of the previous hidden state is the input to the current state, to input to generate the current hidden state. There are two popular RNN models. One is called long short-term memory, LTSM, and gated recurrent unit, GRU. So this is like visualization of like RNN, input of X at time step T, and then the output kind of like flow into the next time step. So if you unroll this picture to the right here, you can see that time step 0, going to RNN, generate the hidden state that go into to generate the next time step. So if we need to generate the next time step H1, we need the input X1 and the previous hidden state to generate the H1. So the next concept is called attention models. Most of these deep learning model achieve pretty good accuracy, but maybe it's a black box after training. We cannot really explain why, how difficulty to explain why the model like predicts certain things. So attention models like give some interpretability in these type of models. The basic idea is to find some weight from these inputs and trying to better understand which part of the input influence the model prediction the most. So that is the general concept. And this general technique and strategy can be applied to CNN and RNN too. So this is kind of the general concept. And so this part here is the RNN. You saw it before in a previous slide. And somehow the attention mechanism, we calculate this attention weight. The weight add up is equals to 1. All these weight add up is equal to 1. And then basically it's a weight to this input hidden states to generate the final context vector. So like by checking the weight, then you can see that like what is which time step has the most influence to your context vector. Okay, the next concept called transformer. So this is the standard attention model heavily rely on RNN, which is sequential in nature. So it has that kind of involved like significant like challenge to training. So which involve like computational and optimizational challenge. That how can we parallelize this operation? So then a simple question come up. It's like, why don't we just compute a context vector over the input X directly? So then there's this concept of like self-attention. So transformer model basically transform the input embedding Xi into a better embedding Zi with the context. Basically, it's a correlation to all other inputs, X1 all the way to Xn. So take a look at this diagram here. So when we try to transform Xi into a better embedding Zi, we trying to see what is the correlation with the first word in the sentence, second word in the sentence, all the way to the last word in the sentence to generate this attention. And then we multiply the attention with the first word of the sentence, attention to the second words of the sentence, the end word, the final word of the sentence, and then we add up these weighted representation of each of the word in the sentence to come up with ZI. Basically, ZI has a lot more information than the input XI by itself, because it combines all the context information around XI. Right? Let's say a sentence has a pronoun of it. You just don't know what when you look at it. It has no. It doesn't give you that much of information, but it can tell you that it actually referred to certain part of the sentence that makes a big difference. And the other concept it introduced is multi-head. Basically, it's just the self-attention calculation, the same calculation, but it just do a few more times, so that to improve the performance of the attention layer. And then the third concept is called position embedding. So that adds some feature to the embedding to indicate the position of that word, so that like when we do the parallel processing, it knows the position of that word. All right, so the final part is like the proposed sentiment classification models. So this is the CNN with attention. So we look at a review, let's say there's no side effect, and we convert it into embedding. So the embedding dimension is D, and N is like number of word in your review, and then we use DC, number of filters to do convolution. So imagine this, we use this this particular filter with like dimension DE K. K can, if K is 1, basically we just look at one word at a time. If K is 2, then we look at 2 words, it's bigram. 3 is like trigram or something like that. And then we just apply this filter across the whole document. And then we generate the output, like one row of output here in the feature map. So one filter generate one row in the feature map after the convolution operation. So that's why the dimension here is the same as number of filter. And then after we get this feature map, we try to calculate the attention. So basically, it's just a weight of each of the column in the feature map, and then we apply the weight to each of the column to generate this final document representation vector. And then we use this document representation vector to go through fully connected layer to do some prediction. So this is a general idea of the CNN with attention. Okay, next one, we propose to use a bidirectional RNN with attention. Let's say our sample review is called no side effect, and then I am happy, right? So we use bidirectional because sometimes when natural language, sometimes like the meaning depends on the the front part of the sentence sometimes depends on the back part of the sentence. So we're trying to stack up the review from the beginning to the end, and from the end to the beginning. So we stack up the first word and the last word together to make, and then go through the word embedding. So that's why this is 2 times the word embedding dimension. And then we go through the GRU, RNN that encode into this hidden layer, which is like 2 times the dimension of the hidden layer. And then we calculate the attention weight and combine the hidden layer and the attention weight to generate the context vector. And then we use the context vector to go through a fully connected layer to get some prediction. All right. So the final proposal is through transformer. So let's say the same review, no side effect. We kind of convert it into the embedding, and then we add some position embedding, and you can see that like it's like 3 different arrows. Basically, this parallel processing. All these are parallelly processed, and then we go through these transformer blocks. There are several of them, and each block basically is those self-attention mechanism that I talk about, and multi-head, self-attention, and then we get the output, and we do some like max and average pooling to generate the document vector, and then send to the fully connected layer to get prediction. All right, that's about it for my presentation. It's a little bit long, and hope you enjoy it. And thank you.